Okay, Dr. Simon Hunt using a 2 megapixel VTech Kiddie video camera. Quick demonstration of a Stirling cycle engine. Stirling cycle engine essentially is a fixed volume of air that you heat and cool. Looking first of all at principles, if I put this here, this is just a tin can with a balloon on the top of it with an elastic band. As the volume of air heats up, the air expands, and when I zoom in a minute, you'll be able to see that the balloon has risen slightly. So we are getting some force out of this closed volume of air. If I want to contract the air, I simply cool it down, and the balloon goes back down. Again. Now we can expand this principle if we have something to cool it down, a cold side, and something to heat it up, being a hot side, say a flame. Essentially, we're at Stirling came up with the idea of moving a closed volume of air between a cold plate and a hot plate to let it expand or contract to take force out to create motion. Simplest way of doing this is to get a closed volume, say in a tin Spritzer drinking can, use some kind of displacer. This is just an Oasis that you put your flowers in. With the Oasis down at the bottom, if I cool this top face and heat the bottom face, most of the air is at the top, so it'll be near the cold face, so it will contract. If I move it up, most of the air is at the bottom, near the hot flame, so it will expand. Now as I lift this up and down, I can create a positive pressure as it expands, or reduce or negative pressure as it contracts as the air goes towards the cold face. In this particular example, I've got a little bit of tubing that I can put a power piston on to create a mechanism that can not only move the displacing piston, but also create some rotational power. Okay, the simplest way, and this is scaled up a little bit. Here you have a closed body of air in the bottom chamber. Again, I've got a displacer inside here that comes up and down. When the displacer is up at the top, most of the air is at the bottom, so it'll get heated by the flame. If the displacer is at the bottom, most of the air is at the top, so it will be cooled by the air. And on this, I have a power piston driving up and down that drives a crank that turns and pulls up or down the displacer. Next stage of this, the development. Again, I've got a hot face that I'm going to put down at the bottom by the flame. I've got a cold face which is full of cool water. I've got a power piston that's going to come up and down. Another crank that moves round, and then I've got a flywheel being this CD. Put that down. Okay, let's see it working. There we are. So what we have is, hot side is the flame, cold side is the water. We have a displacer in the bottom side in the closed volume of air that lifts up if you want to heat the air, so most of the air is towards the bottom, near the flame, or pushes down if you want to cool the air, so most of the air is towards the top, which is near the water. Moves around slightly. When the displacer is at the top and the air expands, pressure comes to the power piston, which itself pushes the diaphragm up, which is a balloon. This pushes the crank. As the crank moves, that pushes down the displacer, which means that most of the volume of air is now near the cold side and will contract, and the power piston, of course, goes back down again. The flywheel is there for a bit of inertia to keep the whole cycle going. Now, of course, Stirling cycles, I've made quite a few of them. This one's quite a small one. This is based on a kit from the internet that you can download or you can order if you want to. But you can build them in various forms. There are a number of different types of them. The next one I'd like to show you is based on a moving beam. Okay, the next engine we're going to look at is a beam engine example. We've still got a closed volume of air in the coke can. We've got a displacer that when the beam is high on this end will displace all the air so that most of the air is closer to the bottom end, which is the hot end. If the beam lowers on this side, displaces all the air, so most of the air is at the top, near the cold side, so again, it's being cooled by water. We have a power piston in the middle here, which I'll zoom in a minute. And we have a linkage here, which on the other side turns a set of flywheels. The power piston is pushing against this linkage to give us the force to keep the motion continuing by using that swing of motion, translated through the linkages themselves. A couple of words about Stirling engines. They are very efficient, almost towards the Carnot efficiency mark. They do rely on differential of temperature, and as you'll notice with this one, as the coke can heats up, at the bottom it also heats the top plane, which is the cold water side. As the hot water heats, we have a reduced difference in temperature between the hot side and the cold side. And thus we have a reduced difference in the pressures between the pressure when it's heating up and the pressure when it's cooling down, so we get less power out of it. Also, this one was built with my 7-year-old son, and it's not exactly the most frictionless machine in the world, certainly not the most frictionless one I've built, but it does demonstrate the principles of the Stirling cycle. Again, the idea of moving air from a hot side to a cold side, closed volume of air, and taking out the force, the pressure difference as it expands when it gets hot and contracts as it gets cool. Now, Stirling type engines, hot air engines, have a variety of usages. You can use them in reverse to create a temperature difference. They're used industrially for cryo coolers of superconducting magnets, etc., etc., etc. You can use dishes, mirrors to collect sunlight, focus it on some dark black material which will absorb photon energy, warm up, and use that as your hot plate. You can get up to 1400 degrees that way, and you can just use cool air to cool it down, or a borehole or something like that. So this is just a couple of little projects that I've been working on with my 7-year-old son. I hope you enjoyed them. I'll see about making some more videos for you. Bye.